Hello, and welcome to Sweatin' the Small Stuff with Brian Evans. It has been a long time since I've done another one. The last one was, I think, November, when we did our gambling episode for Dan's grand trip to Las Vegas, and it's been a while, and I've been busy holidays doing a show of my own, and I'm working on it. But then I got a wonderful call from Des, host of many other podcasts on Musings of a Geek, and he said he had a friend who was at San Diego State in the theater department who was working on a production of Copenhagen. He's a directing student. His name is Eli. Say hello, Eli.
Hi, nice to meet you.
And he is doing a directing project for Act 1 of Copenhagen, and he was wondering if he could talk to someone because I did a reading of Copenhagen with Dan for Onstage Playhouse here in San Diego a while ago. This would have been like 5, 6, some odd years ago, and he was wondering if he could talk to me and find out, what's it like, the science and physics involved in that. So I'm turning it over to Eli, where he's going to be asking me questions, and I get to pontificate on my science knowledge. So, Eli, what do you want to know about Copenhagen?
Well, thank you so much, Brian, for meeting me on the Saturday. And so basically, this is part of a combined project I'm in directing to. This is Copenhagen is a 40-minute production for this class, but I'm also in another class of dramaturgy. So I'm acting both as the director and dramaturg for this particular production. So for the podcast, in my class, we have this small project of 10 minutes pre-show introduction for the audience. So this podcast will be mainly aimed to prepare the audience going into the theater to see this very, very exciting and very peculiar play.
Yes. Oh, yes.
Yes.
So for those who may not know, what is a dramaturg?
Mm-hmm. So a dramaturg, we have been talking about what a dramaturg is since the first day of the class. And the definition is not as defined as like a director, you direct, or an actor, you act on stage. It's more a behind the scene researcher for the theater to, I would say, prepare the ground for the show to explore and to solidify why do this play in this particular moment, and what are the perhaps technical details. The dramaturg will help prepare an actor's packet for the actors. If it's for Copenhagen, I imagine the actor's packet will involve a lot of physics and a glossary of terms and phrases that they should be aware of. They don't have to become a rocket scientist by the end of the play, but they should have some ideas of what they're talking about, and that will be part of the dramaturg.
Mm-hmm. So Copenhagen is a play based on it's set in the 1930s. It's been a while since I did it. It's in the 30s, where Niels Bohr and I forget Heisenberg's first name. Werner Heisenberg had a meeting just before Germany invaded Denmark. Heisenberg is a German, Bohr is a Dane, and they were both involved in physics. And indeed, in real life, they actually had a meeting at Niels Bohr's house, and nobody knows exactly what it was that they talked about. It. Both of them survived the Second World War, and they did kind of talk about it, but Bohr was never really that specific about what happened, and Heisenberg kept on changing the story, and so there were questions as to, what were they talking about? Because Bohr ended up escaping to the West, and Heisenberg went back to Germany, and they were both working on the nuclear bomb, and the West got it, and Germany didn't, and so there's all sorts of questions of, was Heisenberg deliberately sabotaging this? Because Bohr was his friend, and blah, blah, blah. So there's a whole lot of stuff. So you're only doing the first act?
Yes, I'm only doing the first act.
So what is it that you need to know? What would you like to know about do you want to know about the physics of it?
I'm actually very interested in what you, as an actor, would want the audience to know going into the theater.
Okay. There's a couple things that might happen. There's obviously there's things like program notes that the audience gets to read beforehand. And in a play like this, you really kind of need to do that because the play, as it's structured, it's very metaphorical because there's only three people in it. There's Bohr, there's Heisenberg, and then there's Bohr's wife, Margaret.
Yeah.
And I saw the production when it was on tour, when it first, I don't think it was the first or second tour when it came through. And it's a very bare stage with just two chairs. And there's questions of when you sit down and when you get up and the orbiting and stuff like that. And so there was kind of a visual concept of the internal structure of an atom, at least of a sort of a hydrogen atom, where you have the nucleus and an electron that's orbiting. Granted, with three people, you have two electrons, and but it's metaphorical, and so therefore you can get into that. So a lot of the play is a bunch of questions about why are we doing this? What are we doing? Why are we even talking about this meeting that nobody seems to know about? I think the whole first bit is they're saying, we're dead, we're ghosts, we're spirits. Nobody even cares about this anymore. Why are we talking about it? So a lot of that mimics what we know about how physics works at a very, very small scale. There's a poem that I recall, and it's old enough that I remember it from when I was in college 20 some odd years ago, and it kind of develops the history of physics over time. And it starts off with, in the beginning there was Aristotle, and objects at rest tended to remain at rest, but objects in motion tended to come to rest. And God looked down upon the world and saw that it was boring. So God created Newton, and suddenly that's how they say. God created Newton, and objects in motion, objects at rest tended to remain at rest, but objects in motion tended to remain in motion, and energy was conserved, and momentum was conserved, and God looked down upon the world and saw that it was conservative. So God created Einstein, and the universe was filled with inertial reference frames, and while some of it was especially relative, some of it was generally so, and God looked down upon the world and decided that he was going to create Bohr, and there was the principle, and the principle was quantum, and while all things were quantized, some things were still relative, and God looked down upon the world and saw that it was confusing. So God was going to create Ferguson, and he would have fielded a theory and unified everything, and all would have been as one, that it was the seventh day and God rested, and things at rest tend to remain at rest. And so that kind of describes how it is that we have understood our science. Aristotle's physics is very straightforward. You just take a look, and whatever it is that happens, that's what happens. And so that's why he said objects at rest tend to remain at rest. You put something down, it's going to stay there. And if you push it, it eventually comes to a halt. And so he had this idea that the natural state of things is to be at rest. But then Newton, and through the work of Galileo, I mean, that little poem kind of skips all over Galileo, and Galileo did an awful lot of stuff, but Newton he certainly develops the mathematics behind it through the calculus of being able to say, no, things in motion tend to remain in motion unless they are acted on by an outside force. But that leads to the question of, if I push the little book along the table, it comes to a stop. How do you explain that? And the answer is, there's this thing called friction, and it slowly bleeds off the energy. You have the energy of motion, and it will keep going. And when we went to the moon, we saw this because there's no air on the moon, and you throw things, and they don't stop until eventually gravity comes along, and they hit the moon and stop. And so that's indeed the way it was. But even Newton had a very linear view of how kinematics works. And by that I mean is that there is no limit to how fast you can go. There is no limit to how much energy you can have, etc. The thing is, like, if you on a train and you throw a ball in the direction of the train, you have both the speed of the train and any speed that you gave the ball, and the ball will go even faster than the train. So that's how it worked. But then we started finding through experiments in light, through Einstein and Heisenberg and Bohr and Lorentz and a whole bunch of other scientists, that it doesn't quite work that way. There is indeed a speed limit, the speed of light. Nothing can go faster than the speed of light, is what they found. So it becomes not a linear universe, but a relative universe. And by that, it means is that even the concept of being at rest doesn't make any sense in a relative universe because you're only at rest relative to something else that and if as long as those two things are moving in exactly the same way, then from one standpoint you're looking at the other, yep, it's at rest, it's not moving compared to me. And we see this on our own thing. I'm on the earth, but the earth is rotating and orbiting the sun, which is orbiting the galaxy, and the galaxy is moving through space, and yet this thing right here, it's not moving because it's sharing all of that other motion with respect to me. So that's a lot of what Einstein was doing with relativity, and that deals a lot with large scale structures. You're dealing with gravity and the size of the universe. Quantum mechanics, on the other hand, goes in the other direction. It's dealing with the really tiny things in the universe, stuff that's on the quantum scale. And by that, I mean, just as there's a speed limit to how big things can be, there also apparently is a lower bound. There's there's a limit to how small things can be, and it's called a quantum, because you either have at least that minimum bit, or you don't have anything at all. So there is no minor things. And so this gets into things like what Heisenberg is very famous for is his uncertainty principle. The Heisenberg uncertainty principle states that you cannot measure the momentum of a particle and its position with infinite precision. And by momentum, that means in what direction is it moving and how fast is it going? That's what momentum is. So the equation is, or it should say, the equation, if I recall correctly, is delta x, which stands for its position, the change in its position specifically. Delta is the physics symbol, it's the little d. It's the physical symbol for change. Delta x for position, and delta rho, which is the variable for momentum. You multiply those two bits together for the amount of change, because if you get more and more precise, that change becomes smaller and smaller and smaller. The product of those two is always greater. And let's see if I remember my physics here. I believe it's h bar over 2, which is Planck's constant, h, divided by 2. And that h is this tiny little small thing, but it does mean you can't get it specific. If you get more precise on one, you necessarily get more imprecise on the other. You can get really accurate positions, but you can't be perfect. And a good way to visualize this is if you take a picture of a car on a racetrack as it's passing you by. If you take it with a regular camera, you're probably going to, if it's going really fast, it'll be very, very blurry as it goes by. So given that you know how long the shutter was open and that sort of thing, you can sort of say, okay, well, the end of the car, because of the blur, was here, and then you can sort of see the smear and see that it was here. I have a pretty good idea of how fast it was going because I know how far that is and I know how long it was. Well, distance over time, that's velocity, and I know the direction it was going. So I have a very good idea about its momentum. But it's smeared across that entire thing. I have really no idea where it was at any given moment. I know that it started here and it ended here, and I have its average velocity, but I don't really have a good idea of where it was at any particular given moment. So what I can do is I can use faster and faster film. And so it opens up the shutter much faster, and that smear becomes less and less and less and less until it freezes. At which point I know exactly where it is, but I can't tell whether or not it's moving or if it's just sitting there. And so that's essentially, in a nutshell, what the Heisenberg uncertainty principle is. Now, how it relates to building an atomic bomb, I'm not a physicist. I'm a mathematician. I used to remember all this stuff way back when, but then that was basic physics, and then I forgot about it because I needed to work on my abstract algebra. So there's that. But that's what Heisenberg was primarily known for. Now, Bohr His work was dealing with the internal structure of the atom itself and realizing with this quantum state that, okay, you have the nucleus of an atom and you have the electron that's on the outside that's around it. And what he realized was, along with a lot of other people, is that there are only certain states that electron can exist in while it's around there. There's what it's called the ground state, which is the lowest amount of energy that it has. And we talked about, when we were talking about the periodic table, when we were talking about the orbital shells, go back and see my old episode about the periodic table. You can deal with that. But for instance, when a photon comes and hits that electron and gives it some more energy, it will jump out. But there's only certain levels that it can jump to. A quantum state of energy, only so much energy can exist for it to think. It can't exist really anywhere in between. Now, what he really found, what we have since discovered, it's not so much that it's absolutely physically impossible. It's just so statistically unlikely for it to exist anywhere except in these certain positions. And that has to deal with, for dealing with a uranium atom, for how it decays, etc., for how much energy you need to use if you take a neutron and you throw it at a uranium atom, how much energy is required for it to hit it in a certain way that it will split. That then generates energy and a couple more neutrons, which can go and hit more uranium, which will then split. You get your chain reaction, and boom, if you don't control it. So that's between those two of being able to determine the exact amount of energy that you need and how it deals with, you can see why the two of them would want to talk to each other, because they're both dealing with, at least from a pure scientific standpoint, what does it mean to be an atom and how does it work and etc. So that sort of process of being able to say the large down to the small, and why we still haven't figured it out yet, because the physics that Einstein developed in order to deal with very, very large scale structures is great. It's why we can get to Mars. It's why we have GPS and can see all the way back through the space telescopes to these galaxies that are at the dawn of the universe. They don't really work very well down at the small scale. And similarly, the physics at the very, very small scale is very, very good. It's why we have things like fiber optics and all that stuff. It doesn't really work at very large scales. And so we're trying to figure out how to get the two together. Now, whether or not Heisenberg and Bohr would have been able to figure this out, hard to say, because a lot of this stuff we didn't really learn until, in the 1960s and the 80s. And even now, they just turned on the Hadron Collider and managed to find the supersymmetry with the Higgs boson and blah, blah, blah. And I'm throwing out a lot of jargon. But if what I wanted to tell the audience, to condense that down, is that from the play's presentation, it may seem like nothing ever gets said. There's an awful lot of talking around a subject rather than actually zeroing in on it. And that was done as a way of dramatizing the concept of, I can't get a solid answer. If I nail down this part suddenly becomes very confusing and we don't know what it is. So if I start paying attention to that and start getting down, this becomes fuzzy again and we don't know what that is. So that's why a lot of the dialogue is questioning without a real answer and going back to rehash stuff that you thought you had already talked about, because now we've got a new piece of information which throws everything off that we had done before. So that's kind of how I would condense all that down, is that there is a science behind it that this is trying to dramatize. Now, that said, pet peeve of mine is people using hard physics to try and explain human psychology. And it doesn't work that way, because one of the common metaphors of the Heisenberg uncertainty principle is that the observer affects the observed. And basically what that means is that if you have a tiny little atom and you're trying to figure out where it is, well, you got to see it somehow. You have to detect it. And the only way that we can detect it is to touch it. And that might be by bouncing a photon off it and then detecting where the photon went or something. It's not like physically touch. but you have to interact with it somehow. But the act of interacting with it, because it's so small, changes it dramatically. And so people seem to think, okay, well, this means people. If I look at you, suddenly you're changing and stuff like that. And there are indeed psychological aspects that if you tell people, I'm watching you, suddenly their behavior changes because they know they're being watched. That's not the uncertainty principle. That it's a nice little, the concept of the observer affects the observed is a lovely metaphor, but we have to remember that it's just a metaphor.
Yes.
And so therefore the play is not a dramatic interpretation of the actual uncertainty principle. It's just using that concept of uncertainty to deal with the psychology of the characters involved. So now that I've rambled on for 20 minutes, what's your next question?
That was fantastic, by the way. There's like a really, I think a lot of times when we think about like physics, like concepts like mathematic equations, we think like it's just there. Like it has always been there and it will forever be there like that. But there's a huge and a very long process of coming to that equation and a very long history with actual people. Working on it.
Yes. There's, I think it was Newton that said, if I have seen further than others, it's only because I'm standing on the shoulders of giants. For science, and indeed almost everything in human endeavor, the only reason that we have been able to get as far as we have and be able to continue on is because of all the work that everybody else did to get us here. So it's not like you can just wake up one day and deal with it. And we see the kids these days. I mean, I realize you're so much younger than I am. And what you know, just kind of starting off because the culture has assimilated all of this work and integrated it into how we talk and how we think and why we say the things we say and how we interact with the way that we do. I'm dealing with the fact that I did not grow up with cell phones and computers. I was there when the very first computer, that Apple II and the TRS-80 and all that sort of stuff, when they were brand new. When, oh my God, I have 256 bytes of memory. Do you know what I could do with 256? Compared to terabytes of storage that we have down there, where a computer that used to be, a gigantic box is now, there's more processing power in this phone than there was in my very first computer, which was a good sized laptop these days. And that didn't even include the monitor because you had to hook it up to the television. So I see that a lot in this where they talk about stuff that came before and how they got to where it is, because that's an awful big thing about dealing with the World War II and why it is that they got to where they were and the decision that needs to be made, the interaction between them that splits them off to say that Bohr is saying this and Heisenberg is saying this, and they have to go back to their respective lives and live with this interaction that happened with them. And so it's very fascinating. I've seen a lot of people, they see Copenhagen and they're like, it's a difficult play. I'm not going to deny it. Having done it, having seen it, I think I get a little bit more out of it because I understand the physics involved, but even my friends who understand the physics sometimes go to this play and it's just like, oh my God. Could something happen? Could please just something happen? And it never does. There is no payoff because we don't know what they talked about. We don't know what it is. And he did not want to, the author did not want to impose anything upon them. He just wanted to speculate. Speculate about what it might have been about and what it could have been. And if they walked down this road, it would have been this kind of thing. But what if it had been that thing? And that gets into the many worlds hypothesis. Interesting. Here's another possibility. Because there is what's known as the Copenhagen interpretation of quantum mechanics. And the reason it's called the Copenhagen interpretation is because Bohr, primarily, he wasn't the only one who came up with it, but he did a lot of the work regarding it. And since he was a Dane in Copenhagen, that's what it's dealt with. It has to deal with the fact that in quantum mechanics, because it's kind of related to uncertainty, because you don't know, you cannot determine what the quantum state of something is until you observe it. And the classic example of this is Schrodinger's cat. Poor kitty. This poor bereft kitty. The idea is that you take a cat and you put it in a box that you can't see inside. And inside the box, you have a poison gas capsule. And it is attached to a radioactive detonator that has a 50-50 chance of going off within the next hour, say. So you wait an hour. Okay, is the cat alive or dead? There's a 50-50 chance that it's thing. And until you actually look in the box, you don't know. And that's what quantum mechanics is a lot. There's an actual experiment called the two-slit experiment where you take a barrier and you cut two tiny little slits in it that are very, very close together. And then you start throwing photons or electrons even at these slits. Now, if you just have one slit, if there's only one thing in there and you take a beam at it, you get it on the other side of it, you get a nice shiny stripe where there's just the one slit. If you have the two slits in there and you shine a beam on it, you get what's called an interference pattern. And we see this all the time in waves because light behaves like a wave. And that's because the waves start interfering with each other, because the ones that go through this thing are pulsing like this, and the ones that go through this slit are pulsing like this. And depending upon how they're pulsing together, some of those pulses will overlap and reinforce each other. Some of them will overlap and cancel each other out. And so on the other side, you get this interference pattern of where they reinforced each other and where they interfered. So now what you can do is you start turning down the intensity of the beam.
So just to recap a little bit, the interference patterns is basically you don't see just two stripes, you see like many stripes.
A lot of stripes. So you see a whole bunch of them. And I will get a picture into this video podcast, but if you're only listening to the audio, thank you for reminding me that. You see this interference pattern of a bright stripe and a dark, and a bright stripe and a dark, and a bright stripe. Now, it's brightest in the middle, and it starts fading off on the other things, but still, you get this, not just two stripes, but a whole bunch of them. So then what you do is you start turning down the intensity. So rather than getting a continual beam of light that has a lot of waves, you have just a single photon going towards the slits. Now, you would think you're only going to get two stripes out of that. It either goes through the one slit or it goes through the other slit. And so therefore you'll get all the stripes that are on the side of one and all the ones that went through the other thing. But instead, you get a full interference pattern. It's as if that single photon is interfering with itself. And that's because of this uncertainty. Because it's being unobserved, it has these two quantum states. We don't know which one it went through. And so it's behaving. It really is behaving as if the one photon goes through both slits at the same time. And because it went through both slits, it starts to interfere with each other on the other side. And you get this interference pattern. It's really, really weird. So that aspect of how do you interpret that? How could we possibly get this? And one interpretation of this quantum is called the Copenhagen interpretation, which means that photon does indeed exist in both states at the same time. The cat is both alive and dead at the same time, and it only resolves itself when you open the box and take a look. Now, I always say the cat itself knows whether or not it's alive or dead, and it's very upset that you put it in a box without any milk. So, but that's another little thing. So, but the thing is, we can actually physically see this. We can see that it does indeed do that. The other common interpretation of quantum mechanics is called the many worlds hypothesis, which says that no, you don't have a single particle existing in two states simultaneously. Instead, you have, every time there's a quantum decision to be made, the entire universe splits into one where it went through one and one where it went through the other. And until we make the observation, that's when we can determine which universe we happen to be in. And that's what collapses it out. And so it's really spooky. It's weird. Now, there's other interpretations of quantum physics to try and deal with that, because both of these concepts will make your head explode. Even the common thing is, like, anybody who tells you that they understand quantum mechanics is lying to you, because even quantum physicists don't really get it, because it's so counterintuitive. Because one of the spooky things is that you can set up detectors on the slits that are minimally invasive upon the photon. And if you turn that on, rather than getting the interference pattern, you get the two stripes. So if you actually watch the photon as it goes through, oh, I'm not interfering with myself. But then, even more spooky, if you destroy that information, the interference pattern comes back. It's just, so yes, and there's no comprehending the concept. And that is really, even though that was done much later, that really is a lot of this piece of this thing of you're observing something and you think you've got it down and it's resolved into the two slits, but as soon as you take away something, it all comes back. And so there's an awful lot of that in this play. So I think as a directing thing, if you can sort of get that sense of, I think we've got it something. But then something has made me lose it. And now everything is a jumble again. And we try and focus on another thing and then everything goes on a jumble. You just need to be very, very careful that you don't leave everybody just floating. And I realize that this is like the third time that I've said this, but that would be my advice to you. Okay? What else would you like to know?
A little bit of a comment. I thought it was tremendously interesting that you mentioned interpretation, because that's kind of not how lay people think of science. Lay people often think of science as this hard fact. That's how we use the word fact and objectivity. And we think of science as something you observe, it's there, it's just that.
Right.
And it tells an universal truth. But what you're saying about quantum mechanics is that you need a theory to understand a certain phenomenon, and depending on the theory, the phenomenon would have different meanings.
There's quantum mechanics, and the mathematics of infinity is sort of another thing, is a place where a lot of people get philosophical about what it is that they're doing. Certain things about science are very much like you said. You take the ball and you throw it, and it has this arc, and it's like that. It's not like, well, if I interpret it in this other way, the ball actually went up as opposed to going down. But even so, in that kind of concept, you can interpret it that the ball is the center of the universe, and it did not fall to the earth. Instead, the earth came up to it. The problem with that is that if you go with that, and there's nothing saying that you can't, it just makes physics an awful lot more complicated. This goes back to the concept of, does the earth go around the sun, or does the sun go around the earth? There's nothing stopping us from having an entire, it actually works, Ptolemaic version of the solar system, where the Earth is at the center and everything goes around it. It's just that then you have to start getting all of these epicycles, so that the sun is going around the Earth, but Venus is going around the sun as it goes around, and everything and then you have to be able to figure out, so why does Mars, or Mercury I should say, why does Mercury, which is going around the Earth, suddenly go backwards every now and again, and that sort of thing. And that's because Mars has to be orbiting in its own little vague orbit of its own as it's orbiting the Earth. You can do that, but the math is so complicated to try and deal with that and come up with an accurate, to be able to say, okay, in 3 years' time, where is Mars going to be in the sky? If you do an interpretation of the Earth as the center of the universe, that's a very difficult question. If you set the sun as the center of the solar system, that becomes a much easier question. And so that's, in some sense, when scientists talk about interpretation, they're really, a lot of times, talking about what makes the math easier to deal with. And if you're going to be doing experiments, you have to be able to get your head around, what is it that I'm doing? Why do I need to perform this experiment as opposed to that experiment? And if I do perform this experiment, what would be a significant result? Because, okay, so I dropped this and it fell on the table. What was it I was measuring again? Why do I care about this and things? So I need to have an interpretation of what it is that I'm doing. And so that's the concept, is that we see an effect. When you do the two-slit experiment, you get the interference pattern, but we need to be able to figure out what's actually happening that causes that to think, because I can do the math. The math is easy to do. You can do the wave equations and measure this and all that sort of stuff and explain perfectly mathematically, but as a concept in my head, and then to be able to, now that I know this is true, what can I do with it? I need to have an interpretation. Is it indeed a question of it's in a superposition? Because if it is this superposition where it's in both places at the same time, can I leverage that? And through the Bell experiment, we have found out that we can indeed leverage this kind of superposition. But then that starts leading into questions of, okay, well, that means information is traveling instantaneously across the universe, and that's not allowed by relativity. So how do we interpret this such that we don't break relativity? Or do we have to break relativity? Is indeed relativity broken such that we need to come up? So that's what we're talking about with quantum mechanics. But since we're humans and we deal with metaphors, we talk about this many worlds hypothesis where we start thinking, okay, well, what does that mean? If there are indeed an infinite number of universes, and because these universes are splitting every time there's a quantum event, that means not just an infinite number of universes, but an uncountably large number of universes. If you take a look at my infinity show, you'll understand the difference between infinity and the continuum and Aleph null and Aleph 1. That type of stuff, it's hard. It's hard for us, and we have to figure out a way to wrap our heads around it. So there's a lot of it is philosophical, and a lot of it is just how can we get the math to work? We have to come up with a way of visualizing it that helps us see what it is that we're doing so that we can actually get an answer. Okay?
Yeah. So I do have a question. Since you worked on this show before, so like you obviously like it to a certain extent.
Yes, to an extent.
To work on it. So why this? Why Copenhagen?
Well, the most simplest reason was that Dan asked me to do it. Dan wanted to do it. He said, Brian, you actually understand this, and you can help me, because I can't remember. I think I was playing Bohr, and he was playing Heisenberg, and so he said, you can explain to me what it is that I'm talking about, because he really liked the show, and it's a cerebral run. And in the theater, there aren't that many shows that deal with science. Arcadia is another one, and that also kind of deals with the question of superpositioning and relativity. It's more relativity. It's not really as deep down into the sciences as, say, Copenhagen is. It's more using relativity as a metaphor rather than actually talking about the science. But this is one that actually deals with real people talking about the science. I think Picasso Le Panagile has Picasso and Einstein talking to each other. So from someone who has a science background as well as a theatrical background, to be able to work into a piece that really deals with hard science and while uses it as a metaphor, actually talks about it and tries to, even if it's in its own small way, carry that information to people who are not scientists and help them understand what this is. That appeals to me very, very much. That's part of the reason that I do these podcasts, is because while not every single podcast that I've done has been about the sciences, a lot of them are. And this is one reason that I really wanted to get you on. There's like, we get to talk about my theater side, yes, and talk about these details and why they're so important. Because paying attention to theatrical details when doing a theatrical piece, you have to do that. And so you need to be able to understand what is the subject of what we're talking about, and what do I want my audience to be able to get out of it. And one of that is indeed to help humanize the scientists, the fact that they were dealing, a lot of people, we had sort of talked about this before we got started. I have a degree in math and another one in the arts. And if I were to ever go back to school, I'd probably get a degree in sociology to talk about the interrelationship between the arts and the sciences, because people don't view them in the same way. They use them in their things, but the way people deal with science, kind of as you say, people see science as this very hard, regimented, disciplined, it's this way, and it's the only thing that can be done. And therefore, a lot of people see scientists as cold and heartless and emotionless and not having this thing. And one of the big things in Copenhagen is the possibility that Heisenberg understood what it would mean if Germany got the bomb. And did he sabotage that effort because he was one of the big scientists on the German thing to deal with that. And you take a look at his work, and he is making very fundamental errors that someone of his expertise should not have been making. One of the things is that when you make a uranium fission bomb, you don't just take a hunk of uranium and whack it really hard and hope that it explodes, because the neutrons that come in will have too much energy. And the reaction won't happen. And if there's too much energy, the substance just falls apart, and you have to contain the reaction. So you need to have a mediator that absorbs some of the energy of the neutrons so that they hit in a particular way. And there's lots of things that you can do with it. For an actual nuclear reactor, they use graphite rods. They've got water. There's a lot of water in there to help regulate this. He insisted on using heavy water. Now, heavy water is made out of deuterium. Deuterium is an isotope of hydrogen where instead of having just a single proton and a single electron, it's got 2 protons. Deuterium. So, and there's also tritium that's got 3 protons in there as well. But deuterium is 2 protons and a single electron going around, or it's, is it 2 protons? I think, no, it's not 2 protons. Sorry. It's a proton and a neutron, because 2 protons would be a helium nucleus, and that's completely different. So everything is that. It's a proton and a neutron, and that's what makes it electrically neutral, because it's got the one positive charge and the one negative charge. But it's heavy because it's got a neutron, and a neutron is just as big as a proton mass-wise. So it's heavier. It doesn't have the same absorption rate as regular water does. You would want to use regular water in a nuclear reactor for if you're just generating power and that sort of thing. And yet he was insisting, because they were doing experiments on making a nuclear reactor before they got to the bomb, because in order to understand how to make the bomb, you need to understand how fission works. To understand how fission works, it helps to have a nuclear reactor where you can control the reaction. So he was insisting upon using this deuterium-based water. Why? Someone as smart as he is should have known. No, you don't want to use deuterium. You want to use like beryllium or graphite or just plain water. That would do an awful lot. Did he know? Did he know what it was that there was going? And it would mean the death of people like Bohr and his friends and that sort of thing. But then there's questions of, afterwards, he has all of these conflicting stories about what it was that they were talking about and this. Is he trying to save face to the German people to say that I wasn't a traitor? I just screwed it up. And so you have all of these conflicting things of going in there. And that, I think, is one of the big things to learn about Heisenberg through this play, is that question of why did he do what he do? And even if we will never know why, there's a whole bunch of very human reasons for why it might have happened. It might have been that he just made a mistake, because people latch onto ideas, and I'm certain that this is absolutely the way that it has to work. And because when the bomb went off, when Hiroshima went off, he was quoted as saying, no, it wasn't a uranium bomb. It was just some American thing has pulled a fast one on everyone, because the only way to make a uranium bomb do that, you would need tons of uranium to do this, because that's not the way uranium works. Was he just being wrong? Was he wrong? Was he being consciously wrong? If he was consciously wrong, why was he consciously wrong? Is it because he his ego? Listened? Right? Was he being listened to? Was concerned about being a traitor? Was it just ego? I know that I'm right, and how dare someone prove me wrong? There's all sorts of human reasons for that. And then similarly with Bohr, there's the question of, can I get you out? Do you really understand what it is that you are asking of me? And if I help you, what does that mean? Did Bohr understand what it is? So therefore, did he deliberately send Heisenberg down the wrong path to say, no, you need to, because we don't know what they talked about. So it could be that Heisenberg came to him with questions and Bohr gave him wrong answers. And even then, is it because Bohr didn't know what he was talking about? We don't know. But that's a big thing about Copenhagen, is that we're dealing with this question of, we are doing something that has the potential of killing everybody on the planet, when we set off the nuclear bomb, we had no idea whether or not it would ever stop. Oppenheimer says, "I have become as death," and though I think that was with the hydrogen bomb rather than the uranium, the A bomb, the H bomb. But even so, it's this question of, we don't know if it's going to stop. We're throwing all of this energy. We might set the atmosphere on fire and kill literally everything on the planet. Are we still going to do this? Do we still have to do this? And that leads into questions of, should we have even built the bomb? Should we have dropped it? And there's a whole lot of ethical questions that came out there. And scientists really do think about this. They really, really do. The fact that their decisions are often wrong doesn't mean they don't care. It's just, you have to keep doing what your not only your ethics and your philosophy, but also, I like this phrase, what your passion is telling you to do. And it's such a theatrical, artsy-fartsy sort of word, and following your passion. But that really is why scientists do what they do. They really care about this stuff. They really want to know. And there's a reason that people get into this stuff. I mean, I find mathematics fascinating. The fact that you can take these very abstract concepts of numbers and manipulate them in these certain ways, and you get these things and they relate to real things in the world. It's amazing to me, and I really, really like it. And that's why I do these things that I do. I'm interested in the science. And as a scientist who's working on these great big things, like, you can indeed conceivably hurt a lot of people with what it is that you're finding, but everything is like that. Everything is a dual-edged sword. Just the concept of an automobile. The ability to use an automobile. We live in Southern California. We couldn't live without a car. And yet, how many people die because of cars that goes through there? Because if you go that fast and you hit somebody, they're going to die. Is it worth it? Is it worth it? And that's an ethical question. And scientists really do think about that. And that's why we have things like, okay, you can make an internal combustion engine that allows your car to go hundreds and hundreds of miles an hour. We see them on the big road races. You're not allowed to have that on the streets because it's too dangerous to actually use. We have the Second Amendment that allows you to have a gun. Well, a gun is very useful for lots of things. For dealing with hunting and protection and stuff like that. But it does mean that you can go out and shoot somebody. Is it worth it? And we have to have these ethical conversations. And that's, in some sense, what that I think is, if you can get that into your thing about Copenhagen, is that it's not so much about the science. You need to know enough science to realize that they are talking about building a weapon that can kill millions of people. What is the ethics of that, and of getting into them discussing, oh my God, do you realize what path we're on? That, I think, is kind of the heart of Copenhagen. And why I like it is that it deals with the deep ethics of science. So there's a lovely little phrase for that.
Thank you so much. I think that's a wonderful note to end on.
Okay, yes, we're getting there. So thank you very much. This has been Sweatin' the Small Stuff with Eli. Thank you very much for this.
Thank you so much.
Hopefully I will have this up real soon now. Of course, why am I saying that? Because if you're listening to it, I got it up. But thank you very much this is Brian Evans with Sweatin' the Small Stuff, where the devil's in the details.